When Chris Massey first started theorising about the construction process involved in building the pyramids, much of what shaped his ideas and then formulated his process was already evident and established. The pyramid precinct was already there, 22 feet wide and 33 feet deep. There was evidence of a canal, and there was a covered causeway. In 450 BC, nearly 2,000 years after the construction of the pyramids, the Greek historian Herodotus travelled to Egypt and visited the Giza Plateau. Here, his guide explained to him that the causeway alone took 10 years to build. But whereas traditional historians view it as a walkway used for ceremonial purposes, Chris saw a pipe, a culvert. Too engineered and far too robust for such a simple function. With these parts of the puzzle already in place, Chris began to construct his own method. The project would begin by putting all of the infrastructure in place. A canal would be dug from the Nile connected to the limestone quarry and as close to the pyramid site as possible. A harbour would be built on the canal and a roofed causeway built from the harbour to the pyramid build area. A moat, that is the precinct, would be dug around the limestone outcrop and filled with water. The workforce would be told that any rock protruding through the water needs chipping off. Once all the protruding stone has been removed, the water level would be lowered and the process repeated. The whole area inside the moat need not be levelled, only around the first metres in. It is imperative the perimeter blocks are precisely level for structural strength, like the perimeter walls of a house. The interior is less important, and there is little need to remove rock only to replace it with blocks. Once the water level has been dropped to around 30 millimeters around the full perimeter of the pyramid base and no rock is protruding, the foundations are level and ready to receive the blocks. As soon as the project starts and infrastructure is being put in place, quarrying and shaping the blocks can begin. An enormous amount of blocks would be completed by the time the pyramid site is ready to accept them. When limestone is first quarried, it is a relatively soft rock which hardens when exposed to the CO2 in the atmosphere. By placing the blocks straight into water after they're released from the quarry face, the stone will stay softer and more easily worked with copper tools. By shaping the blocks in the water surface can be used as a constant level. By moving floats around the blocks, they could be easily turned in the water and all 6 sides levelled and shaped. Furthermore, working in water is also a more pleasant, cool, dust-free environment. The outer casing blocks would be quarried upstream at the quarry at Tura. A groove would be precisely carved into the quarry floor and every block would be placed into the groove during shaping. By using the water surface as a level, every block placed into the groove would produce exactly the same angled face, which would line up perfectly when placed. The casing block angle can be checked by using a simple water level. The quarrying process can take place all year round. Once shaped, the blocks would have floats attached and then left in a store area on the quarry floor. Ideally, the floats would be made from cedar wood. The density of limestone is around 2.5 tonne per cubic metre. When placed in water, each cube displaces 1 tonne of water, so you only need 1.5 tonne of buoyant material attached to float a stone block. Cedar wood has a density of around 500 kilograms per cube, so around 3 cubes of cedar wood would be required to float each cube of limestone. The amount of buoyant material required could be massively reduced by either hollowing out the wood or replacing the wood with more buoyant material. But then, as now, Egypt was not blessed with large forests and an abundance of timber, so the floats would be made from sealed papyrus matting wrapped around inflated animal skins. Papyrus grew in abundance, and the whole population knew how to work it, making everyday products from shoes to curtains with it. Papyrus buoyancy properties were well known and had been used for millennia to make simple rafts. Animal skins were commonly used to store liquids such as wine and water. When empty and inflated, They make excellent floats. By having the floats pre-attached to the blocks, they would float in the water, not on it, so saving thousands of man-hours trying to load the multi-ton blocks on top of unstable rafts. The blocks would require far less buoyant material to float them in the water due to the Archimedes principle of displacement. No blocks will be lost to the river floor due to capsizing, as any block floating low can just have more buoyancy attached. If floating a few tons of stone blocks seems improbable to you, then consider right now we have oil tankers sailing on the oceans weighing several thousand tons. When it comes to size and weight, anything can float. The majority of the pyramid building workforce would have been farmers and only available during the 3-month flood season when their fields were underwater and unworkable. When flood season begins, the Nile would rise and deepen the water in the quarry floor. Thousands of blocks would float up, ready for transportation. Multiple blocks could be roped together and using either men in simple reed boats or cattle on a towpath be dragged up towards the Giza harbour. Leading from the harbour all the way up to the pyramid precinct is a covered causeway. The causeway is like a water pipe and totally filled with water from bottom to top. The bottom of the causeway has 2 gates built into it. The lower gate is level with the water in the harbour, while the upper gate is around 8 metres further up the causeway at a much higher level. The higher gate is closed, sealing off the pipe and holding all the water in above. The lower gate is then opened. Although the upper gate stands on a higher plane than the lower gate, the water will stay in place because it is not exposed to atmospheric pressure. It will act like water in a glass pint pot when turned upside down in a water-filled sink, with the water staying in place even though it's above the sink's water level. Atmospheric air pressure is the equivalent of a 25-foot high column of water. With the bottom gate open, blocks can be floated into the causeway. When the space between the 2 gates is full of blocks, the lower gate can be closed and the upper gate opened. The blocks will then float upwards towards the water-filled precinct. Due to the pressure of water on the bottom gates, an extra pair of gates would be built around halfway up the causeway to reduce this pressure. An endless rope could be threaded through the floor of the causeway and the blocks attached to speed up the flotation through the tube. After levelling the precinct, the moat would be semi-refilled with water. The blocks would float up the causeway and into the water-filled precinct. The first blocks to be placed are Tura-angled casing stones. They would be floated around the precinct and lowered into position along a precise, remarked line. When building a house, the perimeter brickwork is placed first to give the building its precise shape and strength, with the roof sitting on the perimeter brickwork and the majority of the internal wall not being load-bearing. Be it a house or a jigsaw, by starting and joining the perimeter pieces, a uniform shape is made. The interior will be then easily sorted out. The same will apply to pyramid building. Get the outer blocks precisely placed and the structure will have the right shape. The first few layers behind the facing blocks would need to be precisely cut and joined together to give the structure inherent strength. Due to the lower blocks not being raised above the precinct height, larger blocks can be placed, giving a strong foundation to the building. As each block layer is placed, it is checked for level against the water's surface. Adjustments would then be made to the blocks. When a layer has been completed and level checked, more water is added to the precinct moat, making the water deeper, so that the next layer can be floated into position. This process would continue until the water is level with the top of the precinct wall, which was around 8 meters high. When the first few layers have been positioned and are nearly level with the precinct wall, the blocks will have to be raised above the precinct water level. By building a lift shaft onto the side of the pyramid, you would recreate a similar structure to the causeway. Again, build 2 separated gates at the bottom of the shaft, fill the shaft with water, and again close a second gate to hold the water in the shaft. Open the first gate and float in numerous blocks, then shut the first gate, open the second gate, and the block will float up to the summit of the pyramid. To keep water pressure down on the lower gates, every 15 meters or so, additional pairs of gates will be built into the shaft. Here we see blocks floating up the water lift shaft. During the process of building the water shaft, the waste side of a facing block would be used to create a perfect seal, as it already starts at the correct angle. Here we see the process of extending the water shaft as the builders complete a layer of the pyramid. The final facing blocks are moved into place and the temporary wall is extended above. Either mud and masonry walls or a wooden box would be built around and above the lift shaft to form a temporary structure to seal in the water. Here we see an example using the mud and masonry wall. Once the top of the shaft is extended with the mud bricks, it is flooded with water. Because the quantity of water it contains is small compared to the shaft, it doesn't require the same level of reinforcement. Then, each of the blocks needed to create the next level are floated up and into place until the layer is complete. The lift shaft system requires the shaft to be heightened less than a metre for each pyramid level rise, taking relatively little material and time to build, compared to the heightening, widening and lengthening of the traditional ramp theory for each level rise of the pyramid. The shaft wall could be anywhere up to 3 meters thick, circumventing any issues regarding water pressure. Further to this, the shaft would be waterproofed. There are many ways to achieve this given the materials available at the time. These include overlapping animal skins, timber, bitumen bricks, or the most likely solution would be to line the shaft with dried clay plaster, which is then covered with waterproofing animal fats or bitumen, as often used by their neighbours the Sumerians. After a layer is completed, a gully is built around the perimeter of the upper level. It is made watertight by lining the floor and walls of the gully with mud and let the scorching Egyptian sun bake the clay dry. Once dried, the gully can be filled with water. Levels can again be taken and extra mud applied to the gully floor to make minor adjustments. The lift shafts would be extended to join the gully. Blocks can then be floated up the shaft and into the gully and then be floated anywhere around the pyramid. The most difficult part of pyramid building is raising the multi-ton blocks hundreds of feet into the air, which the water shaft does relatively easily. Once the blocks are up to the high level, they could just be pulled on rollers or dragged on a wet mud floor into position. But as water-filled gullies would already be in place to check the structure for levelness, it could be extended and used to float the blocks directly into position. Due to the enormous amount of blocks on the lower levels, a lift shaft would be built on all 4 sides to speed up the erection process. The perimeter casing blocks are floated into position first, and then a small wall is built on top to form a gully. This image shows how the pyramid site would look during erection. A deep water gully would be required if the majority of the floats are stacked on top of the blocks. They could then be positioned tight next to each other as pictured. If, however, the floats significantly sail past the side of the blocks, a shallower gully system could be used and positioned as in the picture. There is significant evidence that spring water bubbled up under the pyramid, fed from the water of the significantly higher Lake Maurus, as a natural spring from the lake lies directly underneath the pyramid. A tunnel could have been built down to improve water flow, and as the pyramid structure rose, internal tunnels were extended to help the water flow to higher levels. As the pyramid got higher, water pressure would slowly reduce, so smaller extension channels were built upwards from the king and queen's chamber to raise the water even higher, to eke out as much water as possible. If this was the case, then the water could have been gravity fed through the interior shafts in the Great Pyramid, filling the upper gullies and shafts. Only the highest few levels would need the water bucketing up. If the spring waters were not available, then lines of people could pass buckets of water up the structure. It is likely that these workers would be shaded by reeds suspended above them to protect them from the heat of the sun. There are multiple ways for raising water, from the manual approach seen here in the picture, or using the shidduth method, as seen here from 19th century Egypt. Or they could even use oxen pulling bucket-laden ropes. As a comparison, a standard domestic outdoor hosepipe can deliver around 15 litres a minute, compared to the 600 litres a minute using buckets. If a 10-litre bucket is passed in 1 second, then 100 litres could be passed in 10 seconds. 600 litres a minute per line. At the higher levels of the pyramid, smaller blocks were used for construction. Therefore, the water shaft would equally reduce in size, using less material the higher we go. Here we see how the completed pyramid would look, without the centuries of wear that we see today. The white limestone of Tura would shine in the sunlight. Here we see the traditional view of pyramid building, with thousands of men dragging staggering weights up an enormous ramp which would take millions of tons of material to construct. Once completed, this enormous ramp would need to be demolished and the material dispersed, compared to the easily demolished lift shafts which could be smashed from above and act like a rubbish chute. Evidence is beginning to surface that lends itself to the theory of using water shafts for moving the blocks to the pyramids. The picture you see here is of a roofed causeway that was discovered near Snefru's bent pyramid. The walls are almost 3 meters in height and 2.5 meters wide. This type of causeway is just like the kind that Chris imagines with his theory. Well, how about this? Here we see the well-preserved causeway at the Pyramid of Unis. Why were the walls built so strong and thick, and such large roof slabs used just to create a walkway? Even National Geographic have posted a story on the discovery of a canal linking the Aswan quarry to the Nile River. Another article in the Telegraph reports that scientists have discovered the secret that allowed Angkor Wat, a famous 1,000-year-old temple complex in Cambodia, to be constructed far faster than should have been possible, using canals. Could this technique have been widespread in the ancient world? Further evidence of the use of water can be found in these photos from John Cagman that show salt in the structure as well as water erosion in the lower chambers. Compelling new evidence is now coming to light that there were significant, large high-pressure springs bubbling up on the Giza plain at the time the pyramids were built. These high-pressure springs were fed by a huge underground aquifer, fed at the time from the faster-running deeper Nile. We also have supporting evidence to the flotation theory in the discovery of connection bosses. As you can see in the image, these bosses have been found on various pyramid blocks, much like the modern day lifting lugs. Because of their orientation, it is clear that they would be used to suspend the blocks from above, as would be the case with flotation. Other evidence that lends credence to the flotation theory is the fact that throughout the pyramid structure, salt and water-based impurity has been found. This points towards the notion that there was a lot of water contained at some point within the pyramid structure. Finally, it has been known for some time that the Great Pyramid has very subtle concave sides. This is only visible with the correct lighting conditions as seen here. Could this be evidence of the water shaft? For a deeper look into the water shaft theory, then please read the book.